Good afternoon, everyone. Thank you for joining us again for our latest edition of the Australian Geometric PDE seminar series. Today we're joined by Devesh Rajpal from ANU. He's going to talk to us about affine boosted Gauss curvature flow. Thank you, Devesh.
Thanks, Tim, for the introduction. This is my third year speaking here. I'm grateful to be speaking in this seminar. And today I'm going to be talking about affine boosted Gauss curvature flow. This is joint work with my PhD supervisor, Ben Andrews. So let's get going. We'll start with definitions first. So let M naught be a compact, smooth, uniformly convex hypersurface. A one parameter family of hypersurfaces is said to evolve by alpha-Gauss curvature flow with initial hypersurface M naught if they satisfy the following PDE. So the speed of a point is equal to its Gauss curvature raised to the power alpha. Alpha is a positive power here. So hypersurfaces are flowing inward. I should say that nu is the outward normal here. So hypersurfaces are flowing inward with, and every point the speed is equal to the Gauss curvature raised to a power alpha. And since we are assuming uniformly convex, so K is positive, which is the determinant of the second fundamental form, kappa 1 till kappa n. So we can raise it to a power. And this is a insuitable parametrization. This is a uniformly parabolic equation. You can study it, apply heat methods, and usually the objective has been to find convergence properties and what is the object it finally converges to, which will be, in our case, the self-similar solutions. One more property from heat flow is that the uniformly convex hypersurfaces will remain uniformly convex throughout the flow. So we don't. So we are fine raising this Gauss curvature raised to power alpha. Okay. A particular parametrization which has been helpful in these convex heat flows is the Gauss map parametrization. And also from Gauss map, you can also, alongside support functions. So support function for a convex body can be defined as a function from sphere to real numbers, which is obtained by, so sigma of z is the supremum of x dot z as x varies over a hypersurface. It's the distance from the half space, from the hyperplane, which has normal z. Also, I mean, this contains all the information about our hypersurface. And using support function, we can also find its curvatures, which is why using this differential operator. So A sigma ij is defined as a covariant derivative in the direction I and j of sigma plus gij sigma, where nabla and g are the standard connection in metric on Sn. And the relation we get is that A sigma is after up to a composition using Gauss map is same as the second fundamental form inverse. So K inverse is the determinant of this operator. And we can also write support function. In support, we can also write Gauss curvature flow in support function formalism, which will be like its partial derivative of sigma will be equal to minus the determinant of A sigma raised to minus alpha. Here the minus is coming only because the determinant's inverse is the Gauss curvature. Anyway, this is starting to look like Monge-Ampere type parabolic PDE because this operator is like a determinant of the Hessian with some additional term, but it is like Monge-Ampere type parabolic PDE on the sphere. We can also study shrinking solutions. Since I'm concerned with compact hypersurfaces, our self-similar solutions will be the shrinking ones. And for those solutions, the self-similar solutions will satisfy this identity. So the support function will be proportional to the determinant A minus alpha, the support function will be proportional to the Gauss curvature raised to alpha. And this is a fully nonlinear elliptic PDE on sphere. It's coming from a parabolic PDE, but you can be independently interested in solving these type of elliptic PDEs as well. Okay, let's go over the known results so far. For alpha equals to 1 and n equals to 1, which is the curve case, this is also same as the curve shortening flow. And Gage and Hamilton have proved, I think it's the wrong citation number. Gage and Hamilton proved that the hypersurfaces, in this case, the curves contract to a point, and the rescaled flow converges to circle, which is kind of the nicest thing this parabolic PDEs can do. And the next task would be to generalize this result in higher dimensions. And the Gauss curvature flow originally was proposed for spheres by Firey as a model of tumbling stone. And he proved that if the initial hypersurface is origin symmetric, which is that if x is there, then minus x should also be there. Then he proved convergence to sphere, the two-dimensional sphere in this case. He was also assuming regularity and uniqueness, but those aspects of the PD were also resolved later. So Andrews in Firey also proposed that this hypothesis should hold without the origin symmetric condition, and this was proved later by Andrews in 1999. Which says that x naught need not be origin symmetric. You'll still have convergence of self-similar solutions, convergence of the rescale flow to a sphere. Next, we'll come to a special exponent of this flow, which is the affine exponent. So for alpha equals to 1 over n plus 2, this is also known as the affine normal flow, because up to a reparametrization, this is same as the flow by this vector. And so k raised to 1 over n plus 2 nu plus some other components in the tangential direction is you can define an affine normal using this formula, where AI will also depend on other curvature quantities. But the property of this vector is that it is invariant under affine transformation, which is that it is invariant under the action of SLN plus 1. And so for this particular exponent, our flow will also be invariant under SLN plus 1 transformations. So it's like SLN plus 1 is acting as a symmetric group instead of SON plus 1, which is what we are used to in Euclidean geometry. So in this case, you shouldn't expect spheres as the only self-similar solutions, because you can just do an affine transformation and get ellipses as well as your self-similar solutions. So, but Andrew was able to prove that convergence to self-similar solution. So the rescaled flow, which I'm denoting by tilde here, the rescaled flow for this affine normal power converges to self-similar solutions. And the self-similar solutions have been classified. This came up in Calabi's work, that self-similar solutions are ellipses. And it came in the context of affine geometry. These are the same objects as affine hypersurfaces, and they are related to the study of this Monge-Ampere equation. So this Monge-Ampere equation also has some affine invariance properties. And Calabi proved that the solutions are ellipses in the case we are interested in, at least for compact things. Okay, now next moving on to higher powers. So alpha bigger than n1 over n plus 2. The expectation was that this flow will also converge to sphere. And it was proved in two parts. First, Andrews, Guan, and Nee proved that alpha GCF converges to self-similar solutions. And by here again, I'll mean the rescaled flow. So xt tilde converges to self-similar solution. Next comes the task of finding out what those self-similar solutions are. And this was done by Brindle, Choi, Daskalopoulos, that spheres are the only self-similar solution. And this was, so at self-similar solutions are more like a static problem. You're solving an elliptic PDE, and this was done using maximum principles mostly. All right, so this finishes the generalized Firey conjecture, which was that for powers bigger than 1 over n plus 2, our flow converges to spheres. And the self-similar solutions are spheres. For the other part, which is sub-affine powers, alpha less than 1 over n plus 2, we shouldn't expect convergence. Andrews proved a result in this direction, that for curves, there is a generic non-convergence phenomena in the set of origin symmetric convex curves. So there exist large open sets in the space of origin symmetric convex curves where this flow doesn't converge. And particularly its isoperimetric ratio was blowing up, which obstructed the flow, which obstructed the convergence of the flow. Nonetheless, we can still consider the question of self-similar solutions, which is like solving a particular elliptic PDE on the sphere. And in this case, non-spherical self-similar solutions are also expected. You shouldn't just expect spheres. For alpha equals to 1 over n plus 2, the affine case, we know ellipses were all the solutions, and higher than that, spheres were the only self-similar solutions. But this was like the threshold, and new solutions will start coming in for sub-affine powers. And so for n equals to 1, we know a complete classification. This was done by Andrews, which is that we know, using ODE methods, we know a complete classification of this elliptic PDE. And in the result also, it confirms some intuition that lower alpha corresponded to more symmetric solutions. So lower alphas mean your PDE is degenerating more and more. And more symmetric solutions are also available. For any bigger than or equal to 2, perturbations of sphere with spherical harmonics with control of isoperimetric ratio along the flow gives non-spherical self-similar solutions. So you take a sphere, linearize the flow with respect to some, and like fix the scaling. Let's say we are linearizing the volume preserving flow. We can look at its eigenvalues and construct unstable perturbations out of it. And if we can also manage to do those unstable perturbations such that the new flow has control of isoperimetric ratio, we can guarantee convergence to solutions which are not spheres. Because this will come later at a point that there are entropies associated to these flows, and using entropies method, one can prove that there exist non-spherical solutions. In particular, for example, for n equals to 2 and alpha in this range, we know the existence of non-spherical self-similar solution with tetrahedral symmetry. Okay, coming to the point of, I mentioned a while back, that entropies do exist for this flow. And we'll see two particular variants here. So by entropy, I'll mean integral monotone quantities for GCF. And the first one is Firey entropy, which can be defined as follows. So suppose the convex hypersurface M is bounding open convex domain omega, and for any point P in omega, which is like the interior of the hypersurface, you can take the support function with P as your origin. So script E alpha M comma P is defined as integral of this quantity sigma minus P dot Z raised to 1 minus 1 over alpha, and then taking an appropriate power and normalizing it with volume. So finally, the entropy is scale invariant quantity. And it's a property of GCF that this entropy is monotone. In this case, in this definition, it will be decreasing along the flow. And as long as your point is contained in the interior of the flowing hypersurfaces. Also, equality is attained if and only if you start with a self-similar solution. There's another interesting entropy, which is the Gaussian entropy, which using Gauss map parametrization, we can think of the Gauss curvature as a function on sphere, and we'll define this integral, which is k raised to alpha minus 1 over z, and this is using Gauss map parametrization, raised to an appropriate power and normalized in volume. And under GCF, this entropy is monotone as well. So its time derivative is decreasing, and strictly decreasing if you're not on a self-similar solution. This is slightly different than the entropies I've given in my previous talk if you have attended, but it's only a change of sign. Okay, so for super affine powers, so for alpha bigger than or equal to 1 over n plus 2, we also have upper bounds on these entropies. I should say, sorry, lower bounds. So for alpha bigger than or equal to 1 over n plus 2, we have lower bounds, which is that these entropies are decreasing, but they can't decrease to 0. So inf of E alpha M over all convex hypersurfaces is bounded below by a constant, a dimensional constant. And the same is true for Gaussian entropy as well. And which is what you should expect if you know monotonicity and convergence to self-similar solutions, is that your hypersurface's entropy is decreasing, and it's going to be that of the self-similar solutions of the flow, which we know are spheres or ellipses. So the entropies are bounded by the entropies of spheres or ellipses. And the other feature was that this is not true for sub-affine powers. For alpha less than 1/n+2, let's say I fix the volume, then there is a relation that the in radius of the hypersurface is roughly an appropriate power of the Firey entropy. This Firey entropy also needs to be made translation invariant, or we need to supremize among each interior point, and we can do that. After doing that, the in radius is roughly an positive power of the Firey entropy. So what this means is that if along the flow, my Firey entropy goes down to 0, then the in radius of the hypersurfaces will also go to 0 along the normalized flows, obstructing convergence. Because if your entropy dips down to 0, then the in radius is also going to 0. Its isoperimetric ratio is going to blow up, and your flow is not going to converge. Okay, so based on the previous discussion, we can do another trick, which I'll come to, and it's related to affine orbit of entropies. So for alpha bigger than or equal to 1/n+2, these inequalities that the lower bounds of entropies are like isoperimetric inequalities. In particular, the inequality for Firey entropy follows from Holder and Blaschke-Santalo inequality, which is that the Firey entropy for the affine power is lower bounded by the one give of the ball. And using Holder, you can prove it. You can prove an inequality for all powers higher than 1/n+2. Similarly, the inequality for Gaussian entropy follows from Holder and affine isoperimetric inequality, which says that the Gaussian entropy for 1/n+2 of any convex hypersurface is greater than or equal to that of the ball. Also, Firey entropy has a geometrical interpretation in terms of polar convex body. So for alpha less than 1, and let's say I fix the scale of my hypersurface using volume. So I fix the volume of the interior to be 1. Then the Firey entropy can be written as an integral of this weight mod W raised to some power integrated on the polar of gamma with respect to P. I should introduce what polar is. So for any convex body and P contained in the interior, I can define its polar with respect to P as the set of all points X, such that X with Y dotted X comma Y minus P is bounded by 1. This is the Euclidean dot product where Y belongs to the original. convex body. So for any point P in the interior, I can consider the polar with that center, and its integral, and this is the standard Lebesgue integral with some weight. So, and the weight is given by 1 by alpha minus n plus 2 integrated over this polar dual. And you can see that the exponent here switches signs. For alpha higher than 1 over n plus 2, it's negative. And for alpha less than 1 over n plus 2, it's positive. So there is some kind of switch happening at the affine exponent. And we'll explore this idea, and we'll try to use this idea in a bit. So for sub-affine powers, it's like we are getting reciprocal of bounded quantities because the exponent is flipping signs. What we can do now instead is that we can look for reverse isoperimetric inequalities, but it has to be done at the cost of looking in the affine orbit. So this can be done for our usual isoperimetric inequalities. We are sticking to the case of convex bodies here. And there is a known example of this kind, which is called Ball's reverse isoperimetric inequality, which states the following. If we take the ratio of area raised to 1 over n over volume raised to 1 over n plus 1, we know this has a lower bound, which is the classical reverse isoperimetric inequality, And the question is whether if we allow ourselves to look at the infimum in the affine orbits, does there exist an upper bound? And which is also true. So Ball proved the following. If for every convex body, we look at the isoperimetric ratio, and we look at its minimum in the affine orbits, then among all convex bodies, this is a bounded quantity. So this would be your usual isoperimetric inequality. Which we know is attained for balls. But there also exists a minima. There also exists another side if you are willing to look in the affine orbits. And the equality here is attained from, this side is attained from balls, this side will be attained from more pointier objects like simplexes. Anyway, there exists an easy bound of this inequality using an argument from Yon, which is, we know the existence of Yon ellipsoids, which provides suitable ratios of ellipses inside and outside your convex body. And we can bound it quite easily in the affine orbit. The sharp constant is an analysis question. So we can do something similar in our entropies. For alpha less than 1 over n plus 2, it's like our entropies, we're switching exponents. And so since we can't find lower bounds in the classical sense, we can look for lower bounds in the affine orbits. And this can be done for a rather large general class of integrals, which need not be monotonic. So here's how we'll do it. We can prove a bound in the affine orbit for a range of integrals. I'll call this E beta. And this is integral of the sigma determinant A raised to alpha raised to minus beta. And this is like standard volume measure raised to an appropriate power and volume normalized. And for particular values of beta and alpha, we'll see how it corresponds to usual known quantities. For beta equals to 1, this is same as the Gaussian entropy, which we have considered before. For beta equals to 1 over alpha, this corresponds to Firey entropy. And although this will not be used in our flow, because alpha equals to 0 corresponds to no flow. But for alpha equals to 0, beta equals to 1 corresponds to surface area, and beta equals to p corresponds to LP surface area. So we have a rather easy formula of these entropies under affine change. So given any t in the affine group SLN plus 1, we can calculate the change of entropy by the action of t, and all of the integrand remains the same. What we gain is a power of t inverse mod z. So this is the absolute value of t inverse applied to that normal, and it's raised to this power beta 1 minus alpha times n plus 2. And you see, if I plug in alpha equals to 1 over n plus 2, this quantity is 0, which means it corresponds to an affine invariant entropy. And what we observed is that this integrand is strictly convex as a function on the affine group if the exponent is positive. So if beta times 1 minus alpha times n plus 2 is positive, there will be a minimum of the integrand. And since we are raising it to a negative power, the final thing will have a supremum. So for any convex body, if the alpha is less than 1 over n plus 2 and beta is positive, using an affine change, T naught, I can bring it to the supremum in the affine orbit. And this quantity, there exists a unique position in the affine orbit related to the supremums of these entropies. And similar to the isoperimetric inequality we considered before, using Yawn ellipsoid and Holder, we can prove that for positive beta, but less than equals to 1 over alpha, these entropies in affine orbit have a lower bound. So at the cost of looking at affine orbits and going to supremums there, we do have a lower bound. And in particular for beta equals to 1 and beta equals to 1 over alpha, this implies that Gaussian Firey entropy have a lower bound in the affine orbit. The next step is how should we use this fact now? And the idea is to come up with an affine boosted Gauss curvature flow, which exploits this lower bound at the cost of looking at in affine orbit. In our case, it is easier to work with Gaussian entropy because it is translation independent. And so there's a much, some of the formulas later are easier than entropies which have sigma in them. Also, I'll need one more definition. So for any smooth uniformly convex hypersurface M, I'll call M subscript G its Gaussian position, which is the unique extremizer in the affine orbit for Gaussian entropy. So Mg maximizes the Gaussian entropy and is contained in the affine orbit of M. And we can associate a special position in affine orbits now. And yeah, we'll call this Gaussian position of M. Leveraging this, we can define the affine boosted Gauss curvature flow. So which states that for sub-affine powers, for alpha less than 1 over n plus 2, the affine boosted Gauss curvature flow, abbreviated as ABGCF, is a one-parameter family of hypersurfaces with the initial hypersurface in the Gaussian position, and it will satisfy an almost Gauss curvature flow. So which is that the flow will have speed in the inward normal direction, same as the Gauss curvature flow, minus k raised to alpha, but I'll need to do some affine corrections. So Xi T is an element of the special linear algebra SL n plus 1, modded out by the special linear algebra of orthogonal group, because we can ignore orthogonal groups. They don't change the geometry of the problem. They don't change the entropies. So we can ignore the orthogonal components. But we need to do these affine correction such that the flow remains in the Gaussian position for all time. And if I start with a Gaussian position, I can find formulas for Xi T such that the flow is in the entropy extremizer in the affine orbit. I can also write this down in support function formalism, which is often easier to deal with in some of the calculations later. And the formula is a bit different. So the time derivative of support function is same as this, minus k raised to alpha, or in this case, minus determinant of a sigma raised to minus alpha. And the affine change for support functions look like this. But this is not too hard to derive. And you can see this, it's a parabolic PDE on sphere. And the Xi here will be same as the Xi here, except here it's a matrix. And to make it a function on sphere, I'll say if Xi AB is the component, then the function on the sphere will be Xi AB, ZA times ZB. And if the trace of this matrix is 0, then this will be a second degree spherical harmonic. It's a harmonic polynomial restricted to spheres. Okay, so an advantage for this flow is that the original entropies which were there for Gauss curvature flow are still available for these flows. In particular, if I'm restricting my flow to be at the Gaussian positions, then the Gaussian entropy is monotone for this flow. Since the affine terms, these terms don't change the entropy. When you calculate E dot, since it's at the critical point with respect to affine changes, this term will have zero derivative. This term won't do anything for the time derivative of Gaussian entropy. So good. We still have some entropies. We still have the same entropies. And again, like in Gauss curvature flow, this entropy will be decreasing under ABGCF. But the other advantage of this flow is that now, because we have restricted our flow to remain in the Gaussian positions, we have a lower bound for the entropy. So it can't dip down to 0. So there is a global lower bound on entropy at Gaussian positions. That is, if I take the class of all convex bodies, look at their Gaussian extremizers, then there's a lower bound. And since entropies are kind of related to isoperimetric ratio, this also implies a bound on isoperimetric ratio throughout the flow, because we are restricting ourselves to Gaussian positions. So we should expect better convergence properties out of this flow, and it is true. The next thing is to control curvatures for this flow, which can be done using similar tricks to the one in Gauss curvature flow. So the upper bound is done same as how Cho's did it. We can use Cho's trick, and instead of considering, we can define the function as this quotient of speed upon the support function, and say we are restricting ourselves to the time where support function has a lower bound, is greater than equal to 2 r naught. Then we can multiply this function by a large negative power of entropy, and we'll see why it's going to be useful. I can calculate the time derivative of this quantity. It comes out as some parabolic equation. So this will be an elliptic operator. There are a bunch of gradient terms here and here. And the task is to control rest of the terms. Okay, so if I look at a space-time maximum of this quantity, which we calculated the time, which we calculated the evolution equation, we get a multiple of this original quantity. I've canceled out the powers of E. So phi, some multiple multiplied by E, some constant E times she, minus beta times the derivative of the entropy. And using some calculations, one can bound the affine corrections in terms of the derivative of the entropies. So she was the affine correction terms, and we have a bound on it based on the time derivative of the entropy. So entropy is decreasing. That's why I put a minus sign here. And if I go back here, there's a she term here and there's an E dot term here. For a large beta, I can cancel this term. I can make, we can ignore the she term as long as I have a large beta. These were like the bad terms coming from affine corrections. And also notice that the entropy is bounded both sides now. It will have an upper bound based on the entropy we started with of the flow, the initial hypersurface, and we just proved that in Gaussian positions, it has a lower bound. So entropy is bounded both sides, and you can cancel out the bad term coming from affine corrections and get a bound, and get a bound on this quotient. But because of isoperimetric ratio, we have a lower bound on support function will also imply an upper bound on support function. And so using that, so support function is also controlled both the sides. You can get an upper bound on K alpha. Once we have crossed out the bad terms coming from affine corrections, you will get a polynomial equation where there will be a linear term here and some term with power little more than the linear term, which implies an upper bound. And together, like similar to how Cho did it, we get an upper bound on the speed, as long as there is a lower bound on the support function. So okay, coming to other part, we also need lower bounds on speed, which can be done as following. So we had some affine correction terms, but if we can cancel these affine terms at the cost of an anisotropic factor. So if I let xt tilde be equal to LT times xt, where LT is a matrix. So LT belongs to GL n plus 1, and we can almost mod out by, I think, orthogonal factors. So we can bring an affine change here and make it satisfy a certain ODE, which cancels the affine corrections terms. The evolution equation of our new hypersurfaces will be almost same as Gauss curvature flow, but with an anisotropic term in the front. And this anisotropic factor can depend on time. Okay, so because we had good estimates on the affine correction term before, we also have good estimates on this anisotropic factor this time. And using a barrier argument, I can find a lower displacement bound, which can be written as, say, sigma tilde z comma t minus sigma tilde z comma 0 is bigger than some constant, depending on the geometry, say here, the outer radius, circumradius of the initial hypersurface, times t raised to some positive power. And it will be true for some time bounded by a constant depending on the circumradius. This is a fairly standard barrier argument, because we had control on the anisotropic factor too. So along with a Smokchik type estimate, so the Smokchik type estimate is done on functions like in this form. So I can create a function by support function, added to time times the speed. And in this case, I'll need to include some powers of entropy as well to cancel out the bad terms coming from the time derivative of anisotropic term. Again, so something similar can be done for original Gauss curvature flow. We have adopted the same idea, but we need the one extra term here, the powers of entropy, to cancel out the bad terms coming from affine corrections. And so for large enough power, we can relate this displacement bounds to speed bounds. So rho times k tilde alpha is bigger than some positive power of time with some constant depending on the geometry, up to also time depending on the geometry. Nonetheless, this achieves a lower bound on the speed. We need to bound one more quantity to get complete control over the curvature. And like in the case of Gauss curvature flow, we can consider the evolution equation of the matrix Aij. Under APGCF, it will have some extra terms, which again, we can cancel out the bad terms using large powers of entropy. And so if I denote R max as the inverse of kappa min, the lowest curvature, and this will be the highest inscribed radius, then it will satisfy also an parabolic equation. I can apply maximum principles on it. And for for beta sufficiently large enough, I can get a bound up to some time. And this is enough. Because entropy is bounded, we can go back and play with those maximums to say that our max is also bounded. So we have bounded the speed from above, from below, and we have also bounded one of the curvature quantities, kappa min, from below. This will imply bounds on all of the kappa i's. Using upper and lower bound, you can also bound kappa max now, which implies that these curvatures for the rescaled flow live in a compact set. And thus the rescale affine boosted Gauss curvature flow has curvature contained in a compact set. So if I fix the scale of my flow now, let's say by doing some volume normalizations, I will have complete control on the curvatures. And using higher derivative estimates, I can bound other derivatives of the hypersurface too. And then an Arzela-Ascoli argument will give you a subsequential convergence to a self-similar solution. And using entropy methods, one can also prove that the self-similar solutions of this flow are same as the self-similar solutions of the original Gauss curvature flow, because they both share the same entropy. And you can look at the flow where the entropy doesn't change, which corresponds to the original self-similar solutions. So we have a new flow even for sub-affine powers at the cost of affine corrections, and it has convergence properties up to a subsequence, which should let us to find new self-similar solutions. That's going to be next. It's a work in progress, and we hope to get a good list of the self-similar solutions for this. I'll conclude my talk here.
Let's thank our speaker. Thanks for taking us through all that, Devesh. Does anyone have any questions or comments they'd like to make at this stage? So I suppose I have a question. I guess there was a lot to unpack there in the last few minutes of your talk, I think. So am I right in thinking that this method gives you convergence to self-similar solutions, but you don't know what they are yet?
No.
Okay. And would you mentioned you'd be keen on actually constructing these things. Are you expecting to use parabolic or elliptic methods to construct these things?
I'm not sure if parabolic methods.
Yeah, I mean, I guess
it's originally an elliptic problem, and we know elliptic problems can be solved using PDEs. That has been the thing for geometric flows.
Yeah, I guess I just meant that since you've got a method to theoretically produce some self-similar solutions, would you pursue this method in order to work out what they are, or do you have to completely abandon this approach and try something pretty new?
I don't know yet. Maybe Ben has a better answer.
Well, we can do some things. So, for example, we know that for the sub-affine powers, these sub-affine Gauss curvature flows, you can start from the sphere and push off in a sort of unstable direction from the sphere. And this flow then guarantees that it will converge to some kind of self-similar solution. In particular, you can have perturbations off the sphere which have certain symmetry.
And it's obvious that it doesn't come back to the sphere in some weird...
Yeah, because of the entropy, right? Entropy is monotonic.
Yeah, of course. Yes.
Yeah. right? So anyway, this would produce, for example, new examples of symmetric self-similar solutions in certain ranges of alpha. That's one thing we can get.
Great. Any further comments anyone wants to make, or more questions? Well, in the absence of any further comments or questions, let's thank Devesh again for taking us through this interesting material.
Thanks, Devesh.
Thanks all. I'll stop recording there.